Okay, let's just dive right in. We're going to take a slightly urgent, kind of investigative look at a massive problem sweeping the tech world right now. I'm sure you've noticed the major ongoing copyright lawsuits popping up everywhere, right? And it's because frontier large language models are scraping just vast amounts of data from the web, completely without consent. But here's the massive challenge. How do you actually prove an AI was trained on your specific data? Well, today in this explainer, we're looking at a pretty groundbreaking statistical framework that is quite literally designed to catch these models in the act. So here's our case briefing for today. We'll start with the forensic dilemma of the AI copyright trap. Then we'll meet the SIGIL framework, explore 5 specific trap strategies, uncover the statistical smoking gun, test it all against paraphrasing, and finally, look at the future of data forensics.
Section 1. The AI copyright trap, the forensic dilemma.
Imagine a classic locked room mystery. The thief breaks in, reads your most valuable, highly sensitive documents, and then, boom, all the evidence completely vanishes directly into a neural network's weights. I mean, that is exactly what happens with unauthorized AI training today. Content owners know for a fact their data was scraped, but right now we basically have an absence of rigorous forensic methods to prove that a specific document was included in a model's training set. So the big question is, how do you prove an AI read your work when it doesn't leave traditional footprints?
Currently, most methods rely on post hoc detection. This essentially means waiting until the model is completely trained and then interrogating it, kind of blindly guessing if it memorized your arbitrary content. It's incredibly difficult because the signal-to-noise ratio is just tiny. But the research we're looking at proposes a totally different approach: proactive injection. So instead of guessing after the fact, you're setting a statistical trap beforehand. Think of it like planting an invisible die pack inside a stack of cash before the bank gets robbed.
Section 2. Meet the SIGIL framework, the invisible die.
The really crucial point here is that content owners can now take control of the forensic signal themselves. This proposed solution is called SIGIL. That stands for Subtle Injection for Ground Truth Inference of LLM training data. And at the very heart of SIGIL are what we call canary sequences. These are completely imperceptible signals embedded into your text or code. If an AI trains on those documents, the canary leaves a permanent, statistically distinctive behavioral signature on the model itself. To human readers or even automated scanners, these canaries are completely invisible. But to the AI, they are permanent stain.
In practice, this rolls out in a very clear chronological process. Step 1, before releasing your document, you inject a small number of these invisible canaries and you store the specifics in a sealed escrow. Step 2, you just release your watermark documents publicly, business as usual. And then step 3, when a suspect AI model is deployed, you probe it with targeted queries specifically designed around your canaries to see if, well, the die pack exploded.
Section 3. 5 strategies to trap AI, designing the beacons.
Okay, so how exactly do you force an AI to memorize something that is totally invisible to a human? SIGIL actually uses 5 distinct strategies, and each one targets a completely different memorization pathway in a transformer model. We've got rare token insertion, where you use a highly unusual real English word. There's canary phrase injection, which uses novel sentences. Syntactic structure watermarks, which subtly invert noun-adjective orders. Semantic topic steering, injecting highly specific factual claims. And finally, code pattern beacons, hiding identifiers inside software code.
Let's actually take a look at how a canary phrase functions in the real world. Consider this example sentence. Quantum-resistant hashing uses the Weinberg transform. Now, to a human reader skimming an article, this looks syntactically perfect, right? It's completely plausible. But semantically, it is a wildly novel string of text. Because it's so incredibly unique, if an AI reads it, it causes disproportionate memorization. It acts like this bright, flashing beacon buried deep inside the model's training weights.
But if we want the absolute strongest trap possible, we actually have to look at code. The research found that embedding unique identifiers inside function docstrings and inline comments, the code pattern beacon, achieves the highest detection power of all 5 strategies. You see, transformer models are known to memorize code far more reliably than they memorize prose. In fact, across the 36,000 simulation trials run for this study, code pattern canaries hit an area under the curve, or AUC, of 0.903, which is absolutely massive. It means they are incredibly powerful at separating innocent models from guilty ones.
Section 4. The statistical smoking gun, proving the theft.
So we know we can trap the model, but how do we prove it in a way that actually matters? Because for intellectual property lawyers, probabilistic guessing is just not enough. You need hard, indisputable evidence. Enter the Membership Inference Score, or MIS. This isn't just a loose heuristic. It is fully grounded in Neyman-Pearson hypothesis testing. And what that means in plain English is that it provides a formally controlled false positive rate. It essentially gives you an exact mathematical proof that is actually suitable for court proceedings, totally ensuring you don't accidentally accuse an innocent model.
When we actually map out the data, the statistical smoking gun becomes glaringly obvious. If you have innocent models that were never trained on the watermarked data, their scores sit neatly right around 0. But models that were trained on the data containing our canaries, they shift massively to the right, pushing well past the formal detection threshold. That dramatic shift is the mathematical proof. That is literally the statistical die pack exploding and catching the AI red-handed.
Section 5. Surviving the paraphrase test, the ultimate defense.
Of course, AI companies aren't just sitting still letting this happen. The biggest defense tactic an adversary can use is to try and scrub the evidence by automatically paraphrasing all the scraped data before training on it. The logic is, if they change all the words, surely the trap is destroyed, right? Actually, no, and this is mind-blowing. Even under 100% paraphrasing, when literally every single sentence is completely reworded, SIGIL still maintains a detection accuracy, an AUC, of over 0.86. The trap survives completely intact. The reason paraphrasing completely fails here comes down to something researchers call semantic leakage. When an AI trains on a text, it doesn't just memorize the exact sequence of letters, it actually absorbs the underlying conceptual associations. So if you use the semantic topic strategy and inject a highly specific, unique claim into your data, the AI associates those deep concepts together in its neural weights. Surface-level rewriting just cannot eliminate that deep conceptual link.
Section 6. The future of data forensics, engineering the perfect trap.
As we look at the engineering required to protect data moving forward, it's really all about a delicate balance. On one hand, we have imperceptibility, how invisible the trap is to humans. On the other hand, we have detection strength, how loudly it rings when probed. Strategies like code patterns and rare tokens live comfortably in what we call the ideal zone. They provide this massive statistical proof while remaining completely, practically invisible to everyday readers.
And to really hammer home just how definitive this framework is, consider this number. 73-1. In forensic statistics, a likelihood ratio over 10 is considered strong evidence. But when deploying SIGIL at just a 10% injection rate on a large 7 billion parameter model, the framework achieves a likelihood ratio of roughly 73-1 in favor of the data having been stolen. I mean, this isn't just a hunch. This provides rigorous proof that goes far beyond a reasonable doubt. It gives content owners real, undeniable teeth in IP disputes.
Which really brings us to the ultimate question for the future of generative AI. As these models continue to just scrape everything in their path, will imperceptible canaries, these invisible mathematical die packs, simply become the new default standard for protecting literally all text and code published on the internet? It definitely seems like the forensics are finally catching up to the technology. Thanks for joining me on this explainer, and I highly recommend diving into the source material if you want to explore the math even further.